So let's go through a sketch of the proof. We defined our domain sigma and the Gauss map G simultaneously. Consider capital N copies of the punctured plane C star, labeled C1 star up through the C sub capital N star. On each C sub k star, we'll consider the meromorphic function, the G sub k of z, equal to the delta k times z times that sum I equals 1 to n sub k, alpha sub k comma I divided by the z minus a sub k comma I, minus the sum I equals 1 to n sub k minus 1, the beta sub k comma I divided by the z minus b sub k comma I. Where that delta sub k, it's a positive real number, and we'll have the sum of the alpha sub ki equal to the sum of the beta sub ki and normalized so those sums both equal 1. So the first equality there, the sum of the alpha sub ki equal to the sum of the beta sub ki, ensures that g sub k of z will have a 0 at infinity. The zeros at 0 and infinity are needed to ensure the Gauss map is vertical at the annular ends. So we're going to take these copies of C sub k star and corresponding Gauss maps on each of them, the G sub k of z's, and we want to combine these together. So for each k equal 1 up through capital N, and each I ranging between 1 and n sub k at each level, we'll identify a small annulus around the a sub k comma I, and the C sub k star, with a small annulus around the b sub k plus 1 comma I and c sub k plus 1 star. So for example, here's our c sub k plus 1 star, our c sub k star. So there's the a sub ki location corresponding b sub k plus 1 comma I location. So we're going to glue together, so I'm going to identify that curve with the inside one, and then this curve with that one. And then we'll glue together correspondingly to get glued together. So doing this for all the k and I defines a compact Riemann surface, sigma. So we'll define the Gauss map G from sigma into the extended complex plane as G of z equal to the square root of r times the G sub k of z if z is in the C sub k star where k is even, and then equal to the 1 over square root of r g k of z if the z is in the C sub k star with k odd. Possible height differentials dh are defined by choosing a canonical basis, the a sub ki, b sub ki, for the homology of sigma, and defining dh such that when we integrate over the a sub ki's of dh, we'll get the 2 pi I times gamma sub ki, gamma sub k comma I being just some real number. So for any of the a sub ki in the canonical basis. So for our prototype surface here, we've got those a sub ki's, the necks, horizontal necks, and then the b sub ki's going through all the necks there, and then we've got the one going through up through the top and back to the bottom. So when r is 0, sigma is a disjoint union of copies of C star, and the accompanying Weierstrass data is data for disjoint minimal surfaces. So let's express the period problem as this f of r comma x equal to 0, where x denotes all the other parameters. So the x will be that alpha comma beta comma gamma comma a comma b. The map r comma x mapped to the f of r comma x, it turns out, and this is the key result, that it extends smoothly to r equals 0. And the f, the period problem at the limit, f of 0 comma x, when r is 0, can be computed directly because then we're splitting into those disjoint noted surfaces on which the period problem can be expressed using residues. So we've got the period problem f of 0 comma x equal to 0 given by the balancing condition related to the horizontal periods of the Weierstrass data around the cat and fiddle necks between the copies of C star and sigma. We can also compute the d2 of f of 0 comma x directly. And the non-degeneracy condition implies that d2 of f of 0, x is invertible. Thus, by the implicit function theorem, for small enough r bigger than 0, there exists a unique x of r such that f of r, x of r will equal to 0, solving our period problem for each small r. Hence, we get a family of embedded W-periodic minimal surfaces with parallel ends. So that gives us our results, producing the W-periodic minimal surfaces with these parallel ends, with the different levels connected by tiny catenoidal necks. We've proven the existence of these surfaces in a neighborhood of the noted limit of each surface. So we could examine what's happening at another of the limit of this type of a surface. So going back to Wey's genus 2 surface, let's see what's happening near another limit of the surface. What we see were happening is that Wey's genus 2 surfaces look like two doubly product Shirk surfaces, so one on the left side, one on the right side, with a singly periodic Shirk surface glued in between. So we could imagine that we could glue these pieces together. So at the limit here, we don't have a noted surface, but we got these pieces, a double product Shirk surface, single product Shirk surface, and another double product Shirk surface. And let's note these double product Shirk surfaces aren't the way they're usually expressed. Here, the ends along here are not parallel to each other. So this is not an embedded surface the way we have it, imagining it here. But we could imagine gluing these pieces together end to end, and possibly using a Tresé regeneration technique to prove the existence of them near this limit. And then from there, we could deal with more complicated minimal surfaces with higher genus with this particular limiting behavior. So genus 2 examples. So this example on the left here is one, I only have numerical evidence of it so far. Here we have the Wey's genus 2 surface and then the Rossmann-Thayer-Wolgemuth genus 2 surface. So note the differences between this one and these two is that we're starting with a different KMR surface. So these two, they're the same building block for the KMR surface. But on this one, those, say, the top ends were shifted over by half of the horizontal period. And also, we can note that the handles on these ones are all halfway between the top and bottom ends, versus the handles here are not symmetrically placed. So this one's a particularly interesting example because it doesn't have that a horizontal symmetry plane. So one question we could ask is, well, how can we prove the existence of this one? And we could also ask, is the moduli space of these examples disconnected? Some genus 3 examples with parallel ends. We conjecture that there are 6 distinct genus 3 surfaces with this limiting behavior, where it's kind of, so as we approach the limit, we've got this W product Shirk on that side. I've got one singly product Shirk piece here, another singly product Shirk piece here, and then W product Shirk on the end over here. And all of them have that same thing. W product Shirk, singly product Shirk, singly product Shirk, singly product Shirk. So the idea is maybe we could glue these surfaces together along the ends of the surface. There, here, and then here. So far that's eluded me how to do that, but still working on it. And then here's a genus 15 example with the same behavior. So we got the standard view here and then kind of viewing it from the top. So then we have double periodic piece there, single periodic piece, single periodic, and so on, bunch of them, and then the last double periodic piece over there. And that's it. Thank you for listening to my talk.